This is the last lesson in solutions. It is called double replacement reactions. Now, we have done these before, but prior to this, we have just identified them. The way we would identify them would be two compounds, switching stuff to make two new compounds. That's a pretty straightforward way of doing the identification, but now we're actually going to be predicting the right side or the products of the reaction. So the first thing we have to do is when we put these things in water, they have to dissolve. If they don't dissolve, the reaction won't happen. So we learned this in the last lesson. When you put NaCl in water, it dissolves and dissociates. So it's going to break up into Na plus 1, which is AQ, and Cl minus 1, which is AQ. Then I take PbNO3, and that is going to dissolve in water as well, and that's going to form Pb plus 2 AQ and 2 NO3 minus ones that are AQ. Now, when the reaction happens, when I take a solution that has the sodium chloride and a solution that has the lead 2 nitrate and mix them together, and what's going to happen is the PBs are going to be able to collide with chlorines, and the sodiums are going to be able to collide with nitrates. And we're going to get a change in the chemicals. That's the double replacement reaction. The issue, what's going to cause this reaction to happen is one of these two new chemicals won't dissolve in water anymore and then would turn into a solid. We will call it a precipitate. All right, so the way we do them is simple. The reaction is going to look like this. The first problem is the example that I just gave you. We are going to trade the metals. We'll swap them. That's the easiest way to do it. And then rewrite them. Now, the first thing we're going to do is I'm going to put the Pb with the Cl and then the Na with the NO3. Now that is clearly not good enough. That's step one. Step one is to swap the ions. Step two is to assign the oxidation numbers. Now the way we do that is we take the pre-made compounds on the left, and then we're going to assign the oxidation states and copy them over to the right. So for this, set it equal to 0. I have a rule for sodium. It's plus 1, so therefore chlorine has to be minus 1. NO3 as a group, table E tells me that it's minus 1. There's two of them, so that means Pb has to be plus 2. If you don't know how to do that, you need to go review how to do that because it's necessary. So now I take those numbers and I copy them over here. Since Pb was plus 2 on the left, it's going to be plus 2 on the right. Chlorine is minus 1, plus 1, and NO3 as a group is minus 1. Now the next thing I'm going to do is I'm going to crisscross the new compounds that I'm making to get the correct formula. So it's not going to be PbCl. It's going to be PbCl2, and it's going to be NaNO3, 1 and 1, so I can be done with that. Now, obviously, you can write them a little bit closer together. I spaced them out because I didn't know what they were going to form. The next thing we do, so that is step 2, and step 3 we just did, is you're going to, now the first 3 steps have to be done in order. Steps 4, 5, and 6, they don't really matter, the order. So I don't really care how you do this. You can balance them first if you like. So to balance this, it's going to be 2, 1, 1, 2. Again, if you don't remember how to balancing, you're going to have to go back and teach yourself that. This is not what this video is about. The next step is going to be to name them. A lot of people will have to review this. The names are going to be sodium chloride, lead 2, nitrate. Now, a couple things as far as why does lead have a Roman numeral? Well, it's simple. Metals that have more than one oxidation state on the periodic table need a Roman numeral. Lead's Roman numeral is, lead needs one, and its Roman numeral happens to be a 2 because its oxidation state is a 2. Sodium only has one oxidation state. It's always plus 1, so it doesn't get a Roman numeral. And NO3, I got the name from that by going to table E and looking it up. It's called nitrate. So that's how I do the name. Now, let me show you an easy way to do this naming. Once you name the 2 compounds on the left, all you have to do is just take the metal part of the name and swap them, and you get the new names. In other words, the 2 goes with the lead, so instead of lead 2 nitrate, over here it's going to be lead 2 chloride, There's lead 2 chloride. And then for the next one, instead of sodium, the sodium is not going to be with the chlorine, it's going to be with the nitrate, so it's just sodium nitrate. I just swapped them. The important part there is to know that the Roman numeral is with the metal, and therefore it's going to follow the metal when you do the change. And then the last step is to figure out which one of these is going to stay dissolved in the water and which one of them is not. So for that, I go to table F and I look them up, and it turns out that NO3s and group 1s, in both cases, no matter which one you look up, they always dissolve. There's no exceptions, so it's going to be aqueous. The halides, they dissolve in water, but Pb+2 is an exception. So this one would be a solid. And so when I mix these two clear liquids together, basically a solid is going to form, and that solid is going to be lead chloride, and then what's left over is going to be sodium nitrate that's going to stay dissolved in the water. And that's it. That's a double replacement reaction. I'm going to do the next two with you, and then the work for this is going to be done on the lab. We're not going to have a CASTLE learning on this. So next one. Switch the metals, rewrite them, assign the oxidation states. CrO4 is a polyatomic, it's -2, calcium's +2, that's why they reduced. NO3 is a polyatomic, it's -1, therefore copper has to be +1. Then do the crisscross method. That goes there, the 1 doesn't have to be written. And then I need parentheses around this, I'm going to double it, and then the 1 for the Ca doesn't get written. Name them. Well, we can balance them first, keep it the same. So for balancing, it's going to be 1, 2, 1, 1. Naming. Just to review, copper needs a Roman numeral. It has more than one oxidation state. Calcium does not. It only has one oxidation state. When I make the two new names, the copper 1 is what gets traded for the calcium, and then I just rewrite them. And so that's the new naming. Be aware, this is a common mistake. Yes, the copper is still copper 1, even though there is 2 coppers in the equation. That is because of the crisscross method. You need 2 coppers to make 1 chromate stable. So that's from crisscross method. The copper, though, however, is still a +1 oxidation state, so the name has to stay +1. You don't change the Roman numeral if the number of coppers change. And then the last part, figuring out which one dissolves in water and which one does not. Nitrates always dissolve. So anytime you have an NO3 and there's no exceptions, it's always going to dissolve in water. Chromates do not, and Cu is not an exception. That's the one that's soluble. Last problem. Trade the metals. Let's rewrite them. So we're going to get assign the oxidation states, +1, -1. Crisscross. This one's done. Balancing. And the last part, naming. Well, the next second to last would be to name them. Notice all I did was switch the metals to create the two names on the right. Neither of them get Roman numerals because neither of them have more than one oxidation state. And the last thing, which ones dissolve in water? Well, in this case, here's the issue. Nitrates always dissolve and halides always dissolve, and Mg is not an exception. So it is also a Q, and so here's the issue. In this reaction, since both products dissolve in water, what you would actually get is no reaction. And the reason is, since neither one of them will come out of the water, then the reaction is just going to look like nothing happened. It would be like if I mixed sugar water and salt water together, I'd have one clear liquid mixing with another clear liquid, and I would have a continuous clear liquid, and you wouldn't be able to tell that anything happened because nothing really did happen. They all stayed suspended in solution. And so these guys actually, if both products are aqueous, you actually get no reaction as a result. So that is the one rule. One of the two products that you're making has to be a solid in water or unable to dissolve in water, otherwise the reaction doesn't happen. So hopefully you stayed and watched till the end to pick that last bit up.